Welcome everyone, and today we are happy to have a talk by Roberto Tateo, and he's going to speak about gravity and TTbar flows in higher dimensions. So let's start.
Okay. First of all, thank you for the kind invitation to present my results. So this is the title. It's Gravity and TTbar Flow in Higher Dimensions. So essentially, it's work done in collaboration with my previous master students. Some of them was also my PhD student in Turin. So here it just a summary, essentially what is what will be the main objective of this research. So I guess all of you know that there is a spatial into dimension. There is a spatial operator, a spatial irrelevant operator, which is called TTbar operator for a historical reason. And this operator was introduced about 20 years ago by Nambu-Goto. So it fulfills a very nice factorization property, and it can be essentially defined also at quantum level. And in some sense, in this sense is integrable in the sense that if you know the spectrum of the undeformed theory at finite volume, then there is an exact flow equation, which is essentially a Borger type equation that would give you, move you, drive the spectrum, the finite spectrum at any value of the coupling constant. Okay, so the definition of this irrelevant operator stayed there for many years till 2016, where two groups started to study more detail. They understood something more important, for example, this flow equation for the spectrum, and due to connection with the string theories, then people, a lot of people started to work on this subject. So there are many papers around, all of them are important in their own way. But for the current seminar, the most interesting result is the one obtained in 2017 by this group. And essentially, they discovered, they found out or proposed with rigorous proof a connection between the unperturbed TTbar matter, which I denote here with SM, so this is the action, coupled to flat JT gravity. And then they proposed and they showed that there was an equivalence also at quantum level, so also the level of the partition function with the pure TTbar perturbation. Okay, so this is an equivalence which holds true at quantum level for the TTbar operator in two dimensions. Okay, and so, oops. Okay, so essentially the main objective of my current research is to try to understand the generalization of this TTbar operator, and in particular of this result in higher dimension. Okay, of course, the main problem is that there are, first of all, many possible generalization of TTbar operator in higher dimension, and we will discuss why we focus on some particular choice of the generalization. And then the other obvious main problem is that although in two dimension we can somehow use integrability and to get exact result about the TT-bar. When at quantum level in higher dimension, this is essentially impossible for the moment. Okay, so essentially the main objective is to generalize this on-shell identity at this level in higher dimension. So the idea, which is, from a certain point of view, might be obvious, but I mean, getting exact result is not at all obvious, and making the connection with something which is a generalization of TT-bar is not obvious, is to start, for example, from an action, a matter action, deformed by a TT-bar-like operator in higher dimension, thinking about classical action, of course, and you couple it with your preferred gravity theory, might be Einstein theory or modified gravity theory, and then the idea is to find through dynamical equivalence, on-shell equivalence, move the perturbation from the matter action to the gravity action. So in this sense, if you do this, so for example, if you start from Einstein gravity on the left-hand side of this equation, you should end up with some theory which is modified gravity, which is a modified gravity theory. Okay, so in principle, this is in general possible. This step is in general possible. You think it must be, I mean, possible to do this in any case, but actually concretely it's very, very difficult. Okay, in most of the to do it in general. Okay, so
sorry, can I add?
Sorry?
Concerning your previous slide, could you please explain lambda 2 is just a cosmological constant, right?
Oh yeah, okay, so this one here, it's the vacuum energy, so essentially the inverse of this lambda 2 is related to the deforming parameter.
Okay.
Okay, so there is a relation between tau is hidden in lambda 2, and in particular, okay, so the correspondence is with 1 over lambda 2 and tau, essentially.
So it's just a number which is related to tau, right?
Yeah, yeah.
And another thing, so this, as far as I know, this Jackiw-Teitelboim gravity is some sort of a topological theory, right?
Yes, yes.
What does it mean for relation between SM undeformed, SM deformed?
Okay, so the TT-bar in somehow is also topological. I mean, we will see it in more detail. So TT-bar essentially is equivalent change of dynamical change of coordinate. I think the two are related in this sense. I mean, the two properties, there is a close relation between these two properties. Okay, and also this is affect gravity, so the field, if you vary with respect to this field phi, then you have to impose r equals 0, so it's somehow it's a flat JT gravity. Okay.
Thank you.
Okay, so what about the TT-bar? As I mentioned, TT-bar was introduced more than, well, about 20 years ago as operator, but it was studied more recently as a flow equation. Okay, so something that move you from the initial Lagrangian and build up a TT-bar deformed Lagrangian. Okay, at classical level, the flow equation is simply this one. So the derivative with respect to the tau parameter, tau is the deforming parameter, is equal to the TT-bar operator, which actually coincide with, apart from irrelevant constant in front of the determinant, to the determinant of the stress energy tensor. Okay, now this together with the definition of the stress energy tensor give you really a flow equation. So suppose you start from your preferred unperturbed Lagrangian without the tau parameter, you calculate the stress energy tensor, and you you take the determinant, you add it to the Lagrangian, you have a new Lagrangian, a new stress energy tensor, and you carry on in this way, you build up the full Lagrangian. Okay, so this is essentially the way we did some years ago, and in which we discover a connection with Nambu-Goto theory and therefore with string theory. Okay, so let's do this for starting from let's say a set of boson, which I describe by this vector 5, and then we can even add a generic potential, okay, which would, I mean, shouldn't depend on the derivative of the field, but only on the field themselves. Okay, so you apply, so you start from this initial Lagrangian, you plug it in this, you solve the scheme. Of course, there are nowadays clever way to do it. As partial differential equation, essentially. And you end up with this Lagrangian here. So you have the first term is a modification of the potential, which also depends on tau. Where tau equals 0, you just get the minus v. And then there is, if v is non-vanishing, then there is a dressing, a local dressing of the coupling constant in this way, or at least we like to think about it as a dressing. Here is essentially the kinetic part of the Lagrangian, so without the potential. Okay, so and so the potential is only either in this tau bar, and then there is an extra term which is defined in this way. Okay, so for example, if you take v equals 0, so 0 potential, then you end up with the Nambu-Goto action. Okay, in this would be in arbitrary dimension in the static gauge. Okay, so this is the connection with string theory and branes, etc., etc. So essentially, there is a strange relation that now we understand much better, or we are, more and more understanding it between this TTbar perturbation and some stuff related to string theory and membrane, etc., as we will see also when we extend this approach in higher dimension. Okay, so this is classical, and there is so everything into dimension, it's also through a quantum level. Okay, but of course we want to move to higher dimensions, so we have to be careful. So from what we learn in two dimension, what is important is essentially the following. So it's also so the community in general, in few groups, discovered that the TTbar perturbation is equivalent to a local change of coordinate. So this is related to the question you made at the beginning. Okay, so what does it mean? It means that I can define a Jacobian, a change of coordinate defined by this Jacobian. Okay, and the component of this Jacobian matrix are of this form. So they have the parameter tau, of course. Here is essentially the trace of the stress energy tensor, and as an off-diagonal term, you have this part related to the kinetic part. When tau is equal 0, I'm assuming I'm going back to the identity transformation. Okay, so suppose you are able to, so this is of course local relation. So suppose you can integrate this relation and find the W coordinate, W and W bar coordinate in terms of Z and Z bar. Okay, then what we know is that you can get the perturb solution of the perturb equation of motion just by a change of variable. Okay, so this is the solution of the integration of the Jacobian relation. So I have, suppose I have entirely W in terms of Z and Z bar defined in this way. So the perturbed solution, which is solution of this, of course, quite complicated equation, is actually equal to the unperturbed solution, so at tau equals 0, on new coordinate, which are dynamical coordinate, which depend on the T and on the various components of the stress energy tensor. So it's a dynamical change of coordinate. It's in general might be very, very complicated, but in some case, like for some certain soliton solution, it can be performed exactly. Okay, so if on the other hand, it's almost obvious from what I said that if you perform this change of coordinate on this complicated equation of motion, then you go back to the initial equation of motion. Okay, so this relation here is essentially identical to this one. Okay. Okay, so then what's happened is the following. So suppose I'm choosing my preferred model, which is Sine-Gordon. I mean, I'm talking about classical solutions. There are soliton solution. In particular, there are also this class called breeder solution, which are periodic in time. And this is the unperturbed solution on the left. And on the right, if I perturb it with positive tau, then you go, these bumps become larger and larger, and the solution become multivalued. Okay. If you go in the other direction, so tau smaller than 0, then these bumps will shrink, but again, also in this case, the solution will become multivalued. Okay. Okay, so this is just to say that we are in 2 dimensions. We learn many things, and there are also applications to pure integrable model in the sense of soliton theory. Okay, so the generalization of this Jacobian matrix to general matter field, and in general, I always think about a set of n boson with a generic potential is just anyway the following. So this is the trace on the diagonal, the trace of the stress energy tensor, or the trace I'll divide by 2, and here are what we usually call the T-bar component of the stress energy when I'm discussing over the stress energy tensor in the Z and Z bar component. Okay, so it is nice that if you try to do second derivative of the Jacobian and look for the off-diagonal derivative, so the mixed derivative, then you get an equality between mixed derivatives. So the Hessian matrix is symmetric because the stress energy tensor, because the conservation law of the stress energy tensor. So if this holds, then it's all this, and vice versa. Okay, so this is then when you want to extend it to higher dimension, this is, you can see that in general, apart from particular configuration that look anyway at dimensional reduction of some configuration, then this doesn't hold anymore because this constraint is not enough to guarantee. Okay, so this tells you that at least this step, this classical step of change of coordinate is no, we don't expect it to exist in our dimension. Okay, but we can learn something, because from the Jacobian matrix, which is defined here, we can build up just the metric associated to this coordinate transformation, and this is the result. So this is a metric which is actually truncated. So So this is, let's call it H, the deformed metric. On the right-hand side, you have the initial flat metric. So essentially, where I'm sitting on a Euclidean coordinate. And then you see that this is quadratic in tau. So there are no other term apart from tau squared terms. So there is a sort of truncation. So it's very simple, okay? But the truncation happens, so H, it's quadratic in tau, so there is some sort of truncation when you do this transformation at tau square, which is, of course, coming from the simple form of the Jacobian transformation, okay? So let's move to higher dimension, and we should forgive about global change of coordinate, well-defined change of coordinate globally, but we can still hope to get a change of the metric. Okay, so the generalization to higher dimension, we use this generalization. So essentially the same type of flow equation. This is an irrelevant operator, and for a reason which are actually, I think they are deep, but we just choose perturbing operator, irrelevant operator, which are quadratic in the component of the stress energy tensor. So they depend on, so in the way I wrote here, they depend on two extra parameters, but actually one of the parameter can be rescaled to 1 by just rescaling tau. So there is only a free parameter in this family of irrelevant operator. Okay, so they are defined in this way. So that just the trace of the stress energy tensor square and the trace of t squared. Okay, so if you set d equal 2, then and you choose a equal b equal 1, then you go back to the TT-bar operator in two dimension, which is, as I said, essentially the determinant of the stress energy tensor. Okay. Okay. Now the idea is that okay, maybe.
Sorry, Roberto.
Yes.
It's Anton here. Just a quick precision. Do you care about integrability when the generalization is clear, but
no, we don't care
about as TT-bar or TT-bar-like integrable deformation or not?
Okay, no, we also lose integrability, of course, but apart again for certain specific configuration. What is surprising, at least from my point of view, maybe not from other people's point of view, is that related to what I'm discussing, you see the emergence of something like nonlinear electrodynamics model, like Bohr-Infeld, which are also related to brains and stuff.
That's the reason I'm asking, because we're looking with Dima at the Super M5 setting, certain one.
Yeah.
I see, but still, maybe in 3 dimensions, if there is a certain perturbation to the topological sector, which
maybe, yeah. There may be spatial sectors, but I think at least what I find a bit surprising is really the emergence of many of the models that were studied, for example, in U1 gauge theory, self-dual U1 gauge theory, and they all behave more or less in the same way. So they enter this scheme, this perturbation scheme, with this generalized TT-bar in higher dimension in a very nice way.
Yeah, sure.
Okay, so
yeah, I see.
Ci sto lavorando.
Okay. Okay. So the idea is that we cannot find a global change of coordinate, but we can find a deformation of the metric. Okay, where more or less keeping some of the property of the TT-bar perturbation in 2 dimensions. Okay, so the flow equation for the metric is the following. So this is the perturbing operator. As I said, it's quadratic in the component of the stress energy tensor, and actually can be always written as the stress energy tensor multiplied by another tensor, which we denote T hat, okay, which is defined in this way. So it's a linear combination of the trace plus the stress energy tensor itself, okay? Now, once you write it in this way, so, and you use the fact that this part here, the stress energy tensor, is defined as the derivative of variational derivative of the action, functional derivative of the action with respect on the metric, you see that it is natural that this part here is related to a variation of infinitesimal variation of the metric itself. Okay, so this is coming simply from this by using this equation. Okay, the second equation here, we need it because we want the evolution of the operator here, or this tensor here, T hat, on the right hand side at any value of tau, because we want to take derivative of the first equation and write a higher order derivative in terms of the lower order ones, okay, using another equation. So the second equation is coming from here, so from the first equation, and from the fact that the variation of S with respect to G is exactly T mu nu, okay? This is a partial derivative. This is a total derivative in the sense that we, in the object here, we are also flowing with the metric, okay? So we are flowing with the metric such that the deform metric will give you, okay, the same equation of motion of the deformed Lagrangian. Okay, and the coefficient, I don't know whether this is clear. All the coefficients here are very simple combination of again of the component of the stress energy tensor in this way. Okay. Next step is to use. Okay, so this is so the previous one is really an exact equation where also the metric can flow. Okay, so then the second step is to do a Taylor expansion around an initial point that could be tau equal tau 0, or generically, or tau equals 0. Okay. Okay, so we do this, we perform this expansion, and here you see the derivative of the matrix. They appear and are evaluated at the initial value of tau 0. So we can get all the information just using recursively the equation I mentioned before. Okay, so for example, and it's actually very easy to solve also. I mean, it's a few lines of mathematical code that can give you 100 of coefficients. So it's a perturbative way, but it's very powerful. I mean, there is no limit on the number of coefficients you can get, but then reconstructing the exact function might be a bit tricky and maybe not possible in general. Okay, but
can I ask a question?
Yes.
So what are the assumptions? What are you assuming about Lagrangian LM? Are you assuming just minimal coupling to the metric and no high derivatives or something like that, or you are not assuming anything?
Okay, so this is, so essentially this at the moment I'm not coupling it with so yeah, okay, so if I'm using a generic metric at the beginning, then it's minimal coupling.
Okay.
Okay. Okay, then, okay, so you can do this, and in principle, as I said, it's really running very fast. It's very quick. You can get essentially any order, up to any order you want. Okay, just a matter of time. But there are, okay, so what is interesting is to study particular example where there is truncation. So if you use this idea for the TT-bar into dimension, you observe truncation at second order, and the result is coincide with what I mentioned already before for related to the change of coordinate. But if you go to 4 dimensions, there are some cases where things are even better because there is truncation at first order. Okay, so it means that the second correction is just 0, and you have only one correction, a linear correction to the metric. Okay, so the first example, okay, and then we also have other cases where we're able to, to guess what will be the sum, the final result, the result. Okay, so the first example, as I said, things simplifying in 4 dimensions, is when one of the parameters is 1/2 and the other it's 1. Okay, and in addition, you need for the truncation to require that the stress energy tensor eigenvalue are degenerate. Okay, so there are only 2 different eigenvalues, each of them with multiplicity 2. Okay, so the matrix we are in 4 dimensions, so 4 eigenvalue, but there is degeneracy in this way. Okay, so if with this degeneracy you can really check that second correction, so tau minus tau square correction vanishes, and then because there is a recursive approach, if that vanishes, all the other term vanishes. Okay, so there is really a neat truncation, and this requirement of degeneracy looks a strong requirement, but it's fulfilled in many physical relevant examples. And as I said, for example, any abelian gauge theory would have this property. Okay, so this includes the Bohr-Infeld and the Maxwell-Bohr-Infeld. Okay, so in particular, when for the Bohr-Infeld, so you start from the Maxwell Lagrangian, you deform it with this operator, and you end up with the Bohr-Infeld action. Okay. And this property, so this degeneracy of eigenvalue, just tell you that this operator actually reduces to a familiar form apart from the square root here appears. Okay. There is something which is starting automatically. Okay, so actually, more recently, we discovered another deformation, another combination of A and B, which make the perturb metric to truncate at first order, and this actually it's much simpler, and this has nice property in any dimension, and without requiring the degeneracy of the eigenvalue, and this is when d equals 4 again, and one of the term is 0. So it's essentially in the perturbing operator only the trace survive, and indeed this flow corresponds to a trace square deformation. Okay, it's much simpler. When you do dimensional reduction, you don't get the TT-bar operator, while in the other case, when you do dimensional reduction from d equals 4 to d equals 2, then you go back to the TT-bar. But still, it's quite amazing that with this operator, the metric truncate in 4 dimensions, and it has a nice form in any dimension. Okay, so the other main observation is that if you perform a change of the metric, directly on the action. So, for example, on the modified action, you change the metric in the action. Then you end up with this form, which is very simple. Again, it's this is the unperturbed action, and you have only this extra term, which is linear in tau again, and this is the Baire operator, so it's a perturbing operator, so it is evaluated at tau equal tau 0. Okay. Actually, we think that this form is valid for any value of the parameter A and B. Okay, and we check it in many cases. We think we have proved that this property is true. Okay, so somehow you can do this from right to left, but also from left to right. So you start from this, so you know what is your Baire operator, you know what is the metric, the deformed metric, and you dress it, and in principle you should get this. Okay, so we have in our papers there is this explicit example with Bohr-Infeld and Maxwell. In principle, you should be able to do it more generally. Okay, so then, okay, when the problem from irrelevant operator is switched to has been switched to a metric problem, then it becomes more natural to couple your matter or your deformed matter to some gravity. Okay, so it could be Einstein gravity, for example, at the beginning. So, and what we notice is that, okay, so this, again, it might be trivial in some sense, part of the details, they are, I think, very, very special, that we were able, in this important example, to move, okay, the perturbations from for example, from Einstein gravity to Ricci-based gravity theory, or start from Ricci-based gravity theory coupled to standard matter to move the perturbation on the other side. Okay, so finding essentially a TTbar-like matter, starting from Ricci-based gravity coupled to normal matter, we can move the perturbation on the other side. Okay, this is again is not a mystery. There are many results some result in the literature. I think that the flow equation we are using is essentially our more powerful approach, and it allows us to understand at a deep level what's going on here. Okay. So let's start from Ricci-based gravity theory. So these are actually dealt in the Palatini framework. Okay, so in the Palatini, so this is essentially the action. It is not in general the Einstein-Hilbert action. It would depend on the Ricci curvature tensor and the metric G in an independent way. So the Ricci tensor only depend on the connection. Okay, so this is the assumption, and then you usually can recover standard gravity by imposing the equation of motion. Okay, we will see. Okay, so the assumption we used is that is requiring that for small k, essentially everything go back to Einstein gravity in the way. Okay, this lambda can be usually set to 0. I mean, we don't need, I think, a classical calculation, and it doesn't make any big difference. Okay. Okay, so once we define this Ricci type, Ricci-based gravity model, then we can just include the matter action. And as far as we know, I mean, it has to be understood better. We can only couple matter which does not explicitly contain the connection. Okay. And it's actually okay. This is actually okay for bosonic and bosonic theory, pure bosonic theories, and also for abelian gauge fields. Okay. Now, starting from that gravity action, so the classical equation of motion are, as usual, obtained by performing variation with respect to the independent field. So, for example, if you make the variation with respect to the metric, then this is equivalent to make the variation with respect to the trace of the Ricci tensor in this way. And then the equation of motion, so the generalization of Einstein equation of motion, have this form here. So they are not Einstein field equation. Okay, so they are more complicated because these are more complicated objects. Okay, in particular this bit here. Okay, and on the right hand side, okay, so we are taking variation with respect to G. So on the right hand side, this is the stress energy tensor of the unperturbed matter action. Okay, so it's defined in this way. In addition, if we take variation with respect to gamma, with the connection, actually we find, or you find that gamma is actually related not to G, but to an auxiliary metric, which is usually denoted, or we denote as H in this way. Okay. So this auxiliary metric is actually defined in this way. So there is a connection, a relation between the auxiliary metric H and the original metric G. And this connection, so this relation, it's in general very complicated. Okay. Okay, so the connection is H compatible, it's not G compatible. Okay. Okay, so this all seems very complicated, but actually in the Palatini frame, it is possible to go back to the Einstein-Hilbert action just essentially through a Lagrange transformation, a Legendre transformation. Okay. So, the procedure is the following. First of all, to arrive to this result, we introduce an auxiliary gravitational action, which on shell, okay, on the equation of motion is equivalent to the previous one. So we introduce this auxiliary field H, and then this additional bit here, and we replace in here the trace of R with the trace of H. Okay, so that if we add to this also the matter action, then we get this one, and now if we perform the variation with respect to the field H, then this is what we get. Okay, so this goes away with this cancel with this. So at the minimum, it fixes that this object here should be equal to H. So on shell, this is what you get. And this proves that actually there is a dynamical equivalence between the two gravity action formulation. This one is the original one, and then is equal to this one on shell, on the equation of the same equation of motion. Okay. Okay, so now we will carry on using this at action, and we just move around a bit. They define it. Okay, so we separate this part here. We contain this object here times the Ricci tensor. This is the symmetrized part for to avoid the introduction, the appearance of ghost degree of freedom. and the other part we store it in this bit here. Okay. Now, from just looking at this, it is clear that we can define a new metric which call H, such that this bit here looks just like the Einstein-Hilbert action term. Okay. Okay, so this is the constraint. So on shell, this is the constraint, which is identical to the one I mentioned before. Okay, so putting all together and rewriting everything in terms of this auxiliary matrix H, this is the Einstein-Hilbert part, and then you have this, which is the standard matter on the metric G, and you have here an extra bit. Okay, so now comparing this term with that, we see that in this term we are using only H. Okay, and in this term we are still using G. So the task is now to rewrite G in terms of H and all the term in terms of H, and find the new a matter which is the form. Okay, so now the parameter kappa, which was initially on the gravity side, is now on the matter side. Okay. Now we can define the stress energy tensor for the deformed matter in this way. And of course, the equation of motion in terms of the deformed stress energy tensor have again the form of the Einstein field equation. Okay, but in terms of H. Okay. So now this is essentially the result that we got now, and this is only talking about the matter sector, the definition of the deformed matter action, which is this one, and it's very complicated here. You have to write, as I said, all in terms of H. But then if we compare this with the property of the TTbar in generalized TTbar in higher dimension, you see that you get, there is a striking similarity. So if you can match this bit here with this bit here, of course, with tau minus tau zero equal to the perturbing parameter kappa, then you have a match between the two. Okay. So in conclusion, I mean, with this reframing, which was already well known in the cosmological literature, we have this property. So we start from this Ricci-based gravity on the left-hand side, standard matter, unperturbed matter, and this is on shell equivalent to Einstein gravity and the form, essentially the form matter. Okay, so the main point is whether there are examples where this deformed matter are TTbar-like matter. Okay, so these are the general objectives. So studying interesting irrelevant deformation. In our case, I think we have a strong reason to believe that this quadratic TTbar deformation are nicer than other cases, and move the perturbation to find modified gravity model, or vice versa. You can start from a modified gravity model, your preferred one, and try to move the perturbation from the gravity side to the matter side. Okay. Okay, so these are some examples. So let's consider abelian gauge theory coupled to Eddington-inspired Bohr-Infeld gravity. So essentially, it's a gravity version of Bohr-Infeld, which has this form. This lambda we can set simply to 1. I mean, it's not difficult to take it generic. Okay? So we perform the transformation, and everything can be written as a ratio between H and G in this way. And this ratio of H and G is actually only the square root of the determinant of 1 minus k, the stress energy tensor. So this is the equation, and then okay. So in general, it's quite complicated. So in general, this is nonlinear. This term here is nonlinear in K, but it's quite striking. And of course, this is because everything is consistent also with the previous part. You know, without gravity, is that this expression here or this expression here is simplified when the matter, so when this editor-inspired Bonhoeffer gravity is coupled to U1 gauge theory. So that might be, you know, mod max or Bohr-Infeld or Maxwell itself, etc. But so in that case, we recovered again the same metric we obtained from the perturbative expansion of this TTbar-like perturbation in 4 dimensions. So the same truncation, the same metric, so everything is consistent. And then using this identity, which is valid only when you have degeneracy, you can immediately see that this series of on-shell equivalence all through. So you start from Eddington-Bonhoeffer inspired theory with parameter tau1, you couple it with the U1, let's say, with parameter tau2, and then you can get rid of this and go back to Einstein-Hilbert, to the Einstein-Hilbert action, and this is simple a shift in the tau parameter. Okay, so this is already very general, and you have this other example. They are part of this essential scheme that you can infinitesimally move the perturbation from the gravity part to the matter, or vice versa in this case. Okay, the other interesting, or what we found interesting example is the one related to the trace square perturbation. And it turns out that this is related to Starobinsky gravity in the Palatini framework. So there are no extra degree of freedom. It's just changing, you know, moving one perturbation from one side to the other without including extra degree of freedom. Okay, so the Starobinsky action has this form. So is Einstein action modified by a quadratic term in the trace of the Ricci tensor in this way, and also from the gravity side. So you solve the equation we got from relating H to G, and then you get the same metric truncation at first order. Okay, so the corresponding flow equation for the matter, okay, is this one. Okay, so you can resolve, you can solve the last equation on this slide here and find immediately the action, the deformed action. Okay, so you can do it in general. Again, I should underline stress that we don't understand fermions, but that's probably due to our poor background on fermion. So, for example, if you have a complex field phi and with a generic potential V, and you couple, you add also, okay, so you couple it with Maxwell. Okay, in this way, this is meaning the standard minimal coupling. Okay, so you can deform this using this trace square perturbation, just solving the equation. Actually, we can also do it just by a change of variable, just by a change of the metric. This is what you get. So you get again a deformation of the potential, a deformation of the action in this way, and this remain untouched because this part here is traceless. So I think was already known in the literature. So, for example, that Starobinsky gravity would not affect this part here, so Maxwell part. Okay, so this result, I think it generalized, and it is actually in full agreement with the cosmology literature. But I think again I should stress that it's a different point of view. I mean, it's I think the flow equation is very powerful. Okay, so we have this final equivalence also for Starobinsky. Okay, so then I think I can give my conclusion. So all the results we obtain agree with cosmological and previous literature. I think, as I said, I think it's there is something that we think is more powerful in our approach. And then, so we explore explicit example where we move the perturbation one side to the other from gravity and vice versa. And I should also say that this TTbar, this quadratic TTbar we used, it's giving you some flow which is much more general, the one that you can just get by comparing the gravity, the form of the gravity action with the form of the matter action. So, for example, if you take a Nambu-Goto, okay, and it is in higher dimension, this is not in the family of TTbar perturbation I'm discussing here, but you can immediately see, due to the equality, the similarity between the two actions, so the Eddy-Tobor-Ilfeld action and Nambu-Goto, that if you start from this combination with tau and minus tau, so it's much more restrictive, you can go always in this. So I think it's less general, but of course, just looking at the form of the two actions, you can get this without doing all the steps, performing all the steps that I did. And indeed, we know from this paper the perturbing operator, so there also exists a flow equation, but the perturbing operator is much more complicated. In particular, there is this square root here, which somehow it's might be, seems to give you problem with analyticity. Okay. Okay, so and then the last step will be to include the fermions in the theory. Okay, yes. So I think I've done. Thank you very much for your attention.
Thank you. Are there any questions?
I have a question, comment, I don't know. So suppose you look at some three-dimensional theory.
Yes.
You do your procedure, but at the same time you can start with, you can assume, say, one compact dimension, compactify to two dimensions. You'll get two-dimensional theory with massless and massive fields.
Yes.
Which you can deform in using two-dimensional procedure.
Yes.
How these two things will compare? So, yeah, so the question is how your flow equation does under dimensional reduction, or is there some way of reinterpreting it?
Okay, so so I understand what you are, pointing at. I don't know. So one of the combination that gives you the Bohr-Ilfeld action, then you can do dimensional reduction, just make the solution independent only on two variable, time and whatever one dimension, and then you go to Nambu-Goto with two fields. Okay. So in general, I don't know what's the result. So if I start from three dimension, so probably there is a way to go again to TTbar into dimension, maybe not. But I don't have explicit examples.
Yeah, we actually for the membrane model we discussed with Fiona Sable in our paper last year. We discussed the difference between studying the same membrane, compactifying on one dimension. You get one set of massless plus massive fields.
Yes, yes, I remember. Yes, I know.
But the TT-bar, but that will not be the structure of TT-bar. The stress tensor for these massive fields it looks different compared to.
Yeah. Okay, so but in your case, you really do a compactification.
Yes.
Is it while instead I just
but my questions might be interesting also to see the difference, not at the level of the action, but on these flow equations. What you do, what's the difference between these two cases?
Yeah, very nice comment. Yeah, thank you.
Yeah, just maybe a small add-up, since we have been discussing similar constructions in the supersymmetric membrane settings with Sorokin. And in principle, with adding this TTbar or TTbar-like or root TTbar that are arising in this mod max context.
Yes.
The point is, I think it might be indeed also interesting in your case, because when you do dimensional reduction, you can lose. In general, I think there is no some unique answer, because you really need to study case by case, because in this mod max, the type of what people try to think of D4D, 2D, you can lose very different properties, starting from supersymmetric or superconformal invariance down to integrability. So
you think you lose it? I didn't know that. Okay.
Yes, but I mean in 2D you do have, but in higher D, I mean it is not guaranteed.
Yeah.
So, but I think at the level of this invested Burgers type equation, I think there is not really understood in your case if there is any relation.
Okay. No.
Like
well, yeah.
Burgers equation and its analog in higher D.
Okay. So, okay. In some cases, we know that we have a sort of Burger-like equation, but it's classical. Okay. So the problem is, we would like to have something quantum, but that, I mean, I think it would be a breakthrough if we were able to get something like quantum. But at a classical level, I think you can get a Burger-like equation. I think it's written in one of our paper with Lux pair and things like that a few years ago.
Yeah, but probably relation between this generic TTbar-like flow equations is not probably clear, right?
No.
In different dimensions.
No.
Or especially after reduction.
Yeah. So it might be that in 3 dimensions there are special cases where, as you say, you have something integrable, like I don't know.
Recently we discussed with Benoit on this holomorphic transitions and downgrading this to 2D. Yeah, that in principle could work, but nobody really, I think, understands what should. Well, there are many possibilities. How would you integrably deform it in higher D?
Yeah,
integrably. The keyword is
Yeah, which is the work with Akali pointing. I mean, with Fiona is studying, I think.
Or something like BF theory. Okay.
So I guess you get something non-local when you do dimensional reduction.
Right.
Still, I mean, it might be very interesting anyway, I think.
Yeah, okay. Anyway, thanks. Yeah.
Any other questions? Maybe you can briefly comment why you use only quadratic in T deformations.
Okay, so one of the reasons we are using only quadratic, okay, so because, I mean, quadratic in T, they came from also, they were proposed by work of Marika Taylor, and they have some holographic, so it seems to be the natural generalization. But this dressing procedure seems to be valid only for quadratic operator. Okay, so this fact that for dressing procedure, I mean that you start from the bare Lagrangian, you just add tau whatever TT-bar perturbation, then you know the matrix, you dress it, and you get the deform action. So this, I think, we believe is only true for this type of perturbation we have. I think we think we have approved, but I think it's under scrutiny whether this is. But at least I think if you do perturbative calculation, you see that that's the case, and then we don't know whether there is some subtlety,
but it's also true. Well, the quadratic perturbation, you can kind of undo, not undo. You can write it as some auxiliary.
Yeah. Bastiatonovich. I think it's it's really related to what Cardi also proposed for this. I think there are many reasons why we think things are simpler, and also also the fact that as I said, many nonlinear electrodynamics models are coming out, which are now in the literature, and I think that's an important part also.
Okay, thank you.
You're welcome.
So I don't know, it seems that Dima wants to ask a question, but I don't hear him. Dima, I cannot hear you. Okay, so yeah, it seems that we have some issues with one question. And since there are no further questions, so thank you very much.
Yeah, welcome.
Yeah, thank you. Thank you.
Thank you for the kind invitation.
Thanks.
Good.